Have you ever wondered what lies beyond our little corner of space? Not just the planets orbiting our sun, but what exists far above and below our entire solar system. Everyone knows about the planets orbiting the sun. Almost nobody knows what exists in the vertical direction up and down from our solar system. And here is a question. If you could rewrite one law of physics, which would you change? And how would it transform the universe? Comment down below. I will pin the most creative answer. Now let's begin. When you think about the solar system, you probably picture the sun at the center, with planets orbiting around it like a cosmic merry-go-round. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Maybe you even think about Pluto, still beloved despite losing its planetary status back in 2006. But here's the thing that most people don't realize. Our solar system doesn't just end at Neptune. It doesn't even end at Pluto. The truth is far more mind-bending than that. Our solar system extends outward in a vast, invisible sphere that reaches nearly halfway to the nearest star, and above and below this cosmic neighborhood, layers upon layers of structure exist that connect us to something far grander than we ever imagined. Let me take you on a journey that starts right here on Earth and ventures outward and upward through regions of space that challenge our understanding of distance, time, and existence itself. First, let's get our bearings. Earth sits about 93 million miles from the Sun. We call this distance 1 astronomical unit, or AU for short. It's a useful measuring stick because once you travel beyond the inner solar system, miles and kilometers become almost meaningless. The numbers get too big, too unwieldy, so astronomers use AUs instead. Neptune, the outermost major planet, orbits at roughly 30 AUs from the Sun. That's 30 times the distance between Earth and our star. Light from the Sun takes about 4 hours to reach Neptune. If you wanted to drive there in a car going 60 miles per hour, it would take you over 5,000 years just to reach Neptune. But Neptune is not the edge. Not even close. Beyond Neptune lies a region called the Kuiper Belt. This is a disc-shaped zone filled with icy bodies, dwarf planets, and remnants from the early solar system. Pluto lives here along with other fascinating worlds like Eris, Makemake, and Haumea. The Kuiper Belt extends from about 30 AUs out to roughly 50 AUs from the Sun. It's like a cosmic junkyard, but one filled with clues about how our solar system formed 4.6 billion years ago. Still, we're only scratching the surface. The Kuiper Belt is just the beginning of a much larger story. As we push farther out, we enter a strange, transitional zone. The solar wind, that constant stream of charged particles blasting away from the Sun, begins to slow down. It collides with the interstellar medium, the thin gas and dust that fills the space between stars. This collision creates a boundary called the heliopause, and it marks the point where the Sun's influence starts to fade. NASA's Voyager 1 spacecraft, launched way back in 1977, crossed the heliopause in August of 2013. It became the first human-made object to enter interstellar space. Think about that for a moment. Voyager 1 traveled for 36 years, covering more than 11 billion miles, just to reach the edge of the Sun's immediate neighborhood. But even Voyager 1 hasn't left the solar system. Not really, because beyond the heliopause, beyond the Kuiper Belt, lies something so vast and so distant that it defies comprehension. It's called the Oort Cloud. The Oort Cloud is a colossal, spherical shell of icy objects that surrounds our entire solar system. Unlike the Kuiper Belt, which is relatively flat and disc-shaped, the Oort Cloud envelops everything in a three-dimensional bubble. It's estimated to begin somewhere between 2,000 and 5,000 AUs from the Sun and extends outward to as far as 100,000 AUs, maybe even farther. To put that in perspective, if you could travel at the speed of light, covering 671 million miles every hour, it would still take you nearly a year and a half to reach the outer edge of the Oort Cloud. The Oort Cloud is home to trillions of icy bodies. Most are just a few miles across, frozen chunks of rock, ice, and organic material left over from the birth of the solar system. Every once in a while, gravitational nudges from passing stars or tidal forces from the Milky Way itself will knock one of these objects loose. It begins a long, slow fall toward the inner solar system. As it gets closer to the Sun, the ice starts to vaporize, creating a glowing tail. We call these visitors comets. Some of the most spectacular comets in recorded history came from the Oort Cloud. These are the long-period comets, taking hundreds, thousands, or even millions of years to complete a single orbit around the Sun. But here's where things get really interesting. The Oort Cloud isn't just above and below the plane of the solar system. It completely surrounds us. So when we ask, what exists above and below our solar system? The first answer is this: an enormous invisible cloud of ancient ice stretching halfway to the nearest star. And we've barely begun to explore it. No spacecraft has ever visited the Oort Cloud. Voyager 1, despite traveling for nearly 50 years, won't reach the inner edge of the Oort Cloud for another 300 years. And it won't exit the outer edge for perhaps 30,000 years. Let that sink in. 30,000 years. That's longer than the entire span of recorded human history. But don't worry, I'm going to make this journey a lot faster for you. Because now that we've established the scale of our solar system, we can start looking at what lies beyond it. And that's where the real magic begins. If you're enjoying this cosmic journey so far, make sure to hit that subscribe button and give this video a thumbs up. It helps more people discover these incredible mysteries. Now let's zoom out even further. Let's leave the Oort Cloud behind and start thinking about the structure of space above and below our solar system on a galactic scale. Our solar system doesn't just float randomly in space. It's part of something much larger, the Milky Way galaxy. The Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped region of stars with spiral arms winding outward from the ends of that bar. Our Sun sits in one of those spiral arms called the Orion Arm or the Local Spur, about 26,000 light-years from the galactic center. The Milky Way is shaped like a disk. Imagine a giant frisbee, but one that's about 100,000 light-years across and only about 1,000 light-years thick in most places. Our solar system sits roughly in the middle of that disk, embedded in what astronomers call the galactic plane. But here's the key question: what exists above and below that plane? The answer involves layers. Beautiful, intricate layers of gas, dust, stars, and mysterious invisible matter that we're only beginning to understand. Let's start with the dust. Interstellar dust might sound insignificant, but it's anything but. This isn't the dust you find under your couch. Interstellar dust is made up of tiny particles, often less than 1,000th of a millimeter across, composed of silicates, carbon, and frozen water. These particles are forged in the hearts of dying stars and scattered across space when those stars explode as supernovae. Dust plays a crucial role in the life cycle of galaxies. It absorbs starlight, re-emits it as infrared radiation, and provides the raw material for new stars and planets to form. In the Milky Way, dust is concentrated in the galactic disk, clustered along spiral arms and within massive molecular clouds. Recent studies using data from surveys like APOGEE, which stands for the Apache Point Observatory Galactic Evolution Experiment, have given us incredibly detailed three-dimensional maps of dust in the Milky Way. Scientists analyzed the light from millions of stars, measuring how much that light was dimmed and reddened by intervening dust. By combining these measurements with precise distance estimates from the Gaia spacecraft, they've built maps showing exactly where dust is located, not just in 2 dimensions across the sky, but in 3 dimensions throughout space. What they found is fascinating. The dust in the Milky Way doesn't form a single uniform layer. Instead, it's structured into 2 distinct components. a thin disk and a thick disk. The thin disk has a scale height of about 81 parsecs. A parsec, by the way, is about 3.26 light-years, so 81 parsecs is roughly 264 light-years. The thick disk has a scale height of about 152 parsecs, or roughly 500 light-years. This means that as you move above or below the galactic plane, the amount of dust decreases exponentially, but it doesn't disappear immediately. Even several hundred light-years above the plane, there's still dust out there, drifting through the void, and intertwined with that dust are vast clouds of gas. The space between stars isn't empty. It's filled with the interstellar medium, a thin soup of hydrogen, helium, and trace amounts of heavier elements. Most of this gas is hydrogen, the simplest and most abundant element in the universe. In some regions, hydrogen atoms exist independently, drifting alone through space. In other regions, they clump together into molecules, forming molecular hydrogen. Where you find molecular hydrogen, you often find molecular clouds. These are the densest, coldest regions of the interstellar medium, and they're the birthplaces of stars. Molecular clouds are absolutely staggering in scale. Some of them contain enough material to form hundreds of thousands, or even millions, of stars. They can stretch across hundreds of light years, and within their cold, dark interiors, temperatures can drop to just 10 or 20 degrees above absolute zero. These clouds aren't uniformly distributed across the galaxy. They're concentrated in the spiral arms, following the same patterns as the dust, and just like the dust, they have a vertical structure. The majority of molecular clouds hug the galactic plane, confined to a layer maybe 300 to 500 light-years thick, but some clouds, particularly those stirred up by supernova explosions or stellar winds from massive stars, can be found farther from the plane. One of the most remarkable things we've learned in recent years comes from detailed surveys of molecular clouds using radio telescopes. By detecting the faint radio emissions from carbon monoxide molecules, astronomers have mapped out the three-dimensional structure of these clouds across vast swaths of the Milky Way. What emerges from these maps is a picture of incredible complexity. The galaxy isn't just a smooth disk. It's filled with structures within structures. Spiral arms, spurs branching off from those arms, giant molecular cloud complexes, smaller cloudlets, dense cores where stars are actively forming. It's a fractal tapestry of matter, woven together by gravity, turbulence, and magnetic fields. And here's something truly humbling. We're part of this tapestry. The sun, the Earth, every atom in your body was once part of this interstellar medium. We are, quite literally, made of stardust. The carbon in your cells, the oxygen you breathe, the calcium in your bones, all of it was forged in the nuclear furnaces of ancient stars and scattered into space when those stars died. Eventually, that material coalesced into new clouds, and from those clouds came our solar system, our planet, and ultimately us. But let's keep moving outward. Let's climb higher above the galactic plane and see what else we find. As we rise above the thin disk of gas and dust, we encounter the thick disk of stars. The Milky Way's stellar disk isn't uniform either. It's composed of multiple populations of stars, each with different ages, chemical compositions, and orbital characteristics. The thin disk, where most of the galaxy's star formation happens today, contains young, metal-rich stars. These stars orbit the galactic center in relatively circular paths, staying close to the galactic plane. The thick disk, on the other hand, contains older stars, typically between 10 and 13 billion years old. These stars have more elliptical orbits and puff up to greater heights above and below the plane. The scale height of the thick disk varies depending on which study you look at, but it's typically somewhere between 600 and 1,000 light-years. This means that even 1,000 light-years above the galactic plane, you'd still find a respectable population of stars, though far fewer than in the plane itself. Recent work using data from the Gaia spacecraft has revolutionized our understanding of the Milky Way's structure. Gaia has measured the positions, distances, and motions of over 1 billion stars with unprecedented precision. By analyzing this data, astronomers have discovered that the Milky Way's disk isn't flat. It's warped, like the brim of a hat that's been left out in the rain. In some directions, the disk bends upward. In others, it bends downward. These warps are likely caused by gravitational interactions with satellite galaxies, like the large and small Magellanic Clouds, which orbit the Milky Way and tug on its outer regions. There's also evidence of vertical waves rippling through the disk, density patterns that propagate up and down like ocean swells. Some of these waves might have been triggered by a dwarf galaxy passing through the Milky Way's disk millions of years ago, sending stars bobbing up and down in its wake. All of this tells us something profound. The galaxy is not static. It's dynamic, evolving, alive with motion and change, but we're not done climbing yet. Let's go higher still. Beyond the thick disk, we enter the realm of the stellar halo. The halo is a roughly spherical cloud of stars that surrounds the entire Milky Way. Unlike the disk, which rotates in an organized way, the halo stars have chaotic, highly elliptical orbits. They dive through the galactic plane, swing out to enormous distances, and then plunge back in again. The stars in the halo are among the oldest in the galaxy, some dating back more than 13 billion years to the very dawn of the Milky Way's formation. They're metal poor, meaning they contain very few elements heavier than hydrogen and helium. This makes sense. They were born in the early universe, before generations of stars had lived and died, to enrich the interstellar medium with heavier elements. The halo extends out to at least 200,000 light-years from the galactic center, perhaps even farther. It's incredibly sparse, though. If you were floating in the halo, you might have to travel dozens or even hundreds of light-years before encountering another star. But the halo isn't just made of stars, it also contains something else, something far more mysterious: dark matter. Dark matter is one of the greatest unsolved puzzles in modern astrophysics. We can't see it directly because it doesn't emit, absorb, or reflect light. But we know it's there because of its gravitational effects. When astronomers measure how fast stars and gas orbit the galactic center, they find that the outer regions are moving much faster than they should be, based on the visible matter alone. The only explanation is that there must be additional mass, invisible mass, holding everything together. This invisible mass forms a massive halo around the Milky Way, extending far beyond the visible stars and gas. Current estimates suggest that dark matter makes up about 85% of the total mass in the universe. In the Milky Way, the dark matter halo probably extends out to at least 600,000 light-years, possibly even farther. So when we ask, what exists above and below our solar system? Part of the answer is this: an enormous, invisible scaffolding of dark matter, holding our galaxy together in a gravitational embrace that we're only beginning to understand. And there's more. Mixed in with the dark matter halo are globular clusters. Globular clusters are some of the most spectacular objects in the night sky. Each one is a tightly packed ball of hundreds of thousands or even millions of stars, all orbiting a common center of gravity. They're incredibly old, with ages typically between 10 and 13 billion years, and they orbit the Milky Way in the halo, far above and below the galactic plane. The Milky Way has about 150 known globular clusters. Some orbit close to the galactic center, while others swing out to distances of hundreds of thousands of light-years. Because they're so old and so distant, globular clusters give us a unique window into the early history of our galaxy, but they also pose a puzzle. The distribution of globular clusters isn't random. Some of them seem to share similar orbits, moving together through space like members of a cosmic convoy. This suggests that they might have originally belonged to smaller dwarf galaxies that were torn apart and absorbed by the Milky Way billions of years ago. The globular clusters are the fossils of those ancient collisions, still orbiting the Milky Way long after their parent galaxies ceased to exist. It's a sobering reminder that galaxies are not isolated islands. They interact, collide, and merge. The Milky Way itself has grown over billions of years by cannibalizing smaller galaxies. And it's still happening today. Right now, as you're watching this video, the Milky Way is in the process of devouring the Sagittarius Dwarf elliptical galaxy. This small galaxy is passing through the Milky Way's disk, and tidal forces are ripping it apart. Streams of stars from the Sagittarius Dwarf can be traced looping above and below the galactic plane, slowly being assimilated into the Milky Way's halo. In the future, something even more dramatic will happen. The Andromeda Galaxy, our nearest large galactic neighbor, is currently rushing toward us at about 70 miles per second. In about 4 billion years, Andromeda and the Milky Way will collide. The two galaxies will merge, their stars, gas, and dark matter halos blending together to form a single larger galaxy that astronomers have playfully nicknamed Milkomeda. When that happens, the question of what exists above and below our solar system will have a very different answer. But that's a story for another time. For now, let's shift our focus. We've talked about the structure of our galaxy above and below the solar system, but there's another layer to this story, one that takes us beyond the Milky Way itself. Let's talk about the space between galaxies. The space between galaxies is called the intergalactic medium, and just like the space between stars, it's not truly empty. For a long time, astronomers thought that intergalactic space was essentially a void, a near-perfect vacuum with almost nothing in it. But over the past few decades, observations have revealed something surprising. Even the vast gulfs between galaxies contain gas, primarily hydrogen, along with traces of helium and heavier elements. This gas is incredibly tenuous. In some regions, there might be only 1 atom per cubic meter. That's far more diffuse than even the best laboratory vacuum we can create on Earth. But when you're talking about the immense volumes of intergalactic space, even that thin haze adds up to a staggering amount of matter. Much of this gas is locked up in something called the warm-hot intergalactic medium, or WIM for short. The DUIM consists of gas heated to temperatures between 100,000 and 10 million degrees by shock waves from supernova explosions, galactic winds, and the gravitational pull of dark matter structures. At these temperatures, the gas is ionized, meaning the electrons have been stripped away from the atoms. This makes the WM extremely difficult to detect because it doesn't emit much visible light. However, astronomers have found ways to study it. By observing distant quasars, those incredibly bright beacons powered by supermassive black holes, and analyzing how their light is absorbed by intervening gas, scientists can map out the distribution of the WIM across cosmic distances. What they've discovered is that the WIM isn't randomly distributed. It follows the large-scale structure of the universe, a cosmic web of filaments and sheets that connects galaxies together. This cosmic web is shaped by dark matter, which acts as the skeleton upon which all visible matter is draped. Imagine a three-dimensional spiderweb stretching across billions of light years. At the intersections of the web, where multiple filaments come together, you find galaxy clusters, massive collections of hundreds or thousands of galaxies bound together by gravity. Along the filaments themselves, you find chains of galaxies, strung out like pearls on a necklace. And in the voids between the filaments, you find vast regions of space with almost nothing in them, just a few lonely galaxies drifting through the darkness. The Milky Way sits within one of these filaments, part of a structure called the local sheet. This is a flattened distribution of galaxies that includes the Andromeda Galaxy, the Triangulum galaxy, and dozens of smaller dwarf galaxies. The local sheet is bounded on one side by the local void, a region of space roughly 150 million light-years across, with very few galaxies in it. So when we ask what exists above and below our solar system on the largest scales, the answer involves this cosmic web, this intricate tapestry of matter woven through the universe by billions of years of gravitational evolution. But let's zoom back in a bit. Let's return to the region directly above and below our solar system, within our own galaxy, and talk about something we haven't covered yet: the high-velocity clouds. High-velocity clouds are massive clumps of neutral hydrogen gas that are moving through the Milky Way's halo at speeds that don't match the normal rotation of the galaxy. Some of them are plunging down toward the galactic plane, while others are being ejected upward, flung out by powerful stellar winds or supernova explosions. These clouds can contain anywhere from a few hundred to millions of times the mass of the Sun. They're detected by radio telescopes that observe the 21-centimeter emission line of neutral hydrogen. When astronomers map the sky at this wavelength, they see not just the hydrogen in the galactic disk, but also these high-velocity clouds scattered above and below the plane. Where do these clouds come from? That's still an open question. Some of them might be gas left over from the formation of the Milky Way, material that never quite settled into the disk. Others might be the remnants of dwarf galaxies that were disrupted by tidal forces. Still others might be gas that was ejected from the disk by supernova-driven galactic fountains, which are rising back up only to eventually fall back down in a cosmic cycle of recycling. One of the most famous high-velocity clouds is called the Smith cloud. It's a massive blob of hydrogen containing enough material to form about 1 million stars, and it's currently plunging toward the galactic disk at over 150 miles per second. When it hits the disk, probably in about 30 million years, it will trigger a burst of star formation, lighting up a region of the Milky Way with newborn stars. The Smith cloud is a reminder that the galaxy is a dynamic, living system. Matter moves in and out, cycling between the disk, the halo, and the intergalactic medium. Stars are born, live their lives, and die, enriching the interstellar medium with heavy elements. Galaxies collide and merge, stirring everything up and creating new structures. And through it all, we're here, tiny specks on a small planet, looking out and trying to make sense of it all. Now, let's talk about something truly cutting edge: the recent discoveries involving interstellar objects passing through our solar system. In October of 2017, astronomers made a historic discovery. A strange, elongated object was spotted tumbling through the inner solar system on a highly hyperbolic trajectory. This wasn't an asteroid or a comet from our solar system. The shape of its orbit made it clear that this object had come from somewhere else. It was the first confirmed interstellar visitor ever detected. The object was named 1I/Oumuamua, which means scout or messenger in Hawaiian. Oumuamua was bizarre in many ways. It was shaped like a cigar or a pancake, depending on which interpretation you prefer, and it exhibited a slight acceleration as it left the solar system that couldn't be explained by the Sun's gravity alone. Some scientists suggested that this acceleration was caused by outgassing, like a comet. Others proposed more exotic explanations, including the possibility that it might be an artificial object, perhaps a light sail from an alien civilization. Most scientists favor the natural explanation, but Oumuamua remains one of the most mysterious objects ever studied. Then, in August of 2019, astronomers discovered another interstellar visitor, 2I/Borisov. Unlike Oumuamua, Borisov was clearly a comet, complete with a bright coma and tail. It gave scientists a chance to study a comet from another star system and compare it to comets from our own solar system. What they found was both reassuring and surprising. Borisov's composition was similar to comets from the Oort Cloud, suggesting that comet formation might be a universal process. But there were also subtle differences, hints that conditions in Borisov's home system might have been slightly different from our own. And now, in 2025, we have a third interstellar visitor, 3I/Atlas. This one is particularly exciting because astronomers have been able to study it with some of the most powerful telescopes ever built, including the James Webb Space Telescope. Webb's observations of 3I/Atlas, published just months ago, revealed something unprecedented: the first mid-infrared chemical fingerprint of an interstellar object. Using Webb's MIRI instrument, scientists detected water vapor, carbon dioxide, and, most intriguingly, methane escaping from the comet. The methane detection is significant because methane is relatively easy to destroy in space through exposure to cosmic rays and ultraviolet radiation. Finding it in 3I/Atlas suggests that the comet's ices have been well preserved, shielded from radiation during its long journey through interstellar space. Webb observed the comet on 2 occasions in December of 2025 as it was moving away from the Sun after its closest approach. The observations showed that water vapor extended far from the nucleus, released from icy grains in the coma, while carbon dioxide and methane were concentrated near the comet's core. Scientists have also been working to trace 3I/Atlas's journey backward through the galaxy, trying to figure out where it came from. By integrating its orbit through the gravitational potential of the Milky Way, taking into account uncertainties in its velocity and the motion of the Sun, researchers have constructed probability maps showing the comet's possible origins. The results are fascinating. 3I/Atlas appears to be kinematically consistent with a thin disk population, meaning it probably originated from a star system similar to our own, somewhere in the galactic disk. However, no stellar flyby within the past 10 million years can account for its trajectory. It seems that 3I/Atlas has been wandering through interstellar space for a very long time, perhaps millions or even tens of millions of years, before finally encountering our solar system. These interstellar visitors are incredibly valuable because they give us a direct sample of material from other star systems. We don't have to travel to those systems ourselves. They're coming to us. And here's the exciting part. We're probably just scratching the surface. As our telescopes get better and our surveys more comprehensive, we'll likely discover more and more interstellar objects passing through our cosmic neighborhood. Each one will teach us something new about the diversity of planetary systems in the galaxy. In fact, some scientists estimate that at any given time there might be dozens or even hundreds of interstellar objects within the orbit of Neptune. We just haven't detected most of them yet because they're small, dark, and moving fast. Future missions like the Vera C. Rubin Observatory, which is expected to begin operations soon, will dramatically increase our ability to spot these cosmic wanderers. Rubin will survey the entire visible sky every few nights, creating a time-lapse movie of the universe. Any object that moves will stand out, including interstellar visitors zipping through our solar system. Imagine what we might learn. We could study comets and asteroids from dozens of different star systems, each one a frozen time capsule carrying information about the conditions in which it formed. We could compare the chemistry of these objects to our own solar system bodies and start to understand what's typical and what's unique about our cosmic home. We might even discover objects that challenge our current understanding of planetary formation. Maybe we'll find comets with exotic ice compositions that don't match anything we've seen before, or asteroids with mineral structures that suggest they formed in environments completely unlike anything in our solar system. The possibilities are endless. and we're living in the era when these discoveries are just beginning to unfold. But let's shift gears again. Let's talk about another phenomenon that exists above and below our solar system: cosmic rays. Cosmic rays aren't actually rays at all. They're high-energy particles, mostly protons and atomic nuclei, that zip through space at nearly the speed of light. They come from various sources, including supernova explosions, pulsars, and even distant galaxies. When cosmic rays strike Earth's atmosphere, they collide with air molecules and create cascades of secondary particles. These particle showers can contain millions of individual particles, all spawned from a single cosmic ray collision. Some of these particles reach the ground, where they can be detected by specialized instruments. Cosmic rays are all around us, constantly bombarding Earth from every direction. They pass through your body right now as you watch this video, though they're so small and pass through so quickly that you'd never notice. Occasionally, one might strike a molecule of DNA in one of your cells, potentially causing a mutation. In fact, cosmic rays are one of the natural sources of background radiation that all life on Earth has evolved to deal with. But where do these cosmic rays come from? And what does this have to do with the structure above and below our solar system? Most of the lower energy cosmic rays that reach Earth are accelerated within our own galaxy. Supernova explosions are the primary suspect. When a massive star explodes, it releases an enormous amount of energy in a very short time, creating shock waves that ripple through the surrounding interstellar medium. These shock waves can accelerate particles to incredible speeds, flinging them out into space as cosmic rays. Pulsars, the rapidly rotating remnants of supernova explosions, can also accelerate particles through their intense magnetic fields. And there's evidence that other sources, like the supermassive black hole at the center of our galaxy, might contribute as well. The thing is, cosmic rays don't travel in straight lines. They're electrically charged, and the Milky Way is filled with magnetic fields that pervade the interstellar medium. As cosmic rays travel through space, they're deflected by these magnetic fields, bouncing around like pinballs. By the time they reach Earth, they've been scattered so thoroughly that we can't trace them back to their original sources. However, the highest energy cosmic rays, particles with energies millions of times greater than anything we can produce in our most powerful particle accelerators, seem to come from outside our galaxy. These ultra-high energy cosmic rays might originate from supermassive black holes in distant galaxies, or from other exotic sources we're only beginning to understand. The fact that cosmic rays come at us from all directions, including from above and below the galactic plane, tells us something important. The sources of these particles are distributed throughout the galaxy and beyond. The universe is a violent, energetic place, and even the seemingly empty space around us is filled with high-speed particles carrying information about cosmic catastrophes that happened thousands, millions, or even billions of years ago. Now, let's talk about another phenomenon, the galactic magnetic field. Magnetic fields are everywhere in the universe. Earth has one, created by the churning molten iron in its core. The Sun has one, generated by the complex motions of plasma in its interior. And the Milky Way has one too, woven through the interstellar medium like invisible threads. The galactic magnetic field isn't uniform. It's strongest in the spiral arms, where the density of gas and stars is highest, and weaker in the space between the arms. The field lines tend to follow the spiral structure, wrapping around the galaxy in graceful curves. Above and below the galactic plane, the magnetic field becomes more vertical, threading through the halo. In some regions, the field lines form loops that arc out of the plane and then dive back down, like the magnetic field lines around a bar magnet. These magnetic fields play a crucial role in shaping the structure of the galaxy. They influence how gas flows, affecting where and how new stars form. They confine cosmic rays, keeping them trapped within the galaxy for millions of years. And they interact with the charged particles in the solar wind, creating a complex boundary where the sun's magnetic influence meets the galactic magnetic field. Understanding the galactic magnetic field is one of the frontiers of modern astrophysics. It's difficult to study because magnetic fields don't emit light directly. Instead, astronomers have to use indirect methods, like measuring the polarization of light from distant stars or studying the synchrotron radiation emitted by high-energy electrons spiraling around magnetic field lines. But the effort is worth it, because magnetic fields are fundamental to understanding how galaxies work. They're part of the invisible infrastructure that holds everything together and governs the flow of matter and energy on galactic scales. Let's take another step outward. Let's talk about what exists in the space directly perpendicular to the galactic plane, straight up and down from where we are now. If you could travel straight up from the solar system, perpendicular to the galactic plane, you'd first pass through the layers we've already discussed: the thin disk of gas and dust, the thick disk of older stars, and then into the stellar halo. But as you continue upward, something interesting happens. The density of stars continues to drop, and eventually, you'd reach a point where the nearest star might be tens of thousands of light years away. You'd be in the outer halo, a sparse region where only the most ancient stars and globular clusters reside. Keep going, and you'd eventually leave the Milky Way's gravitational sphere of influence. You'd enter the space between our galaxy and its satellite galaxies. The Milky Way isn't alone. It's surrounded by dozens of smaller galaxies called satellite galaxies or dwarf galaxies. The most famous of these are the Large and Small Magellanic Clouds, visible from the southern hemisphere as fuzzy patches of light in the night sky. These two irregular galaxies orbit the Milky Way at distances of about 160,000 and 200,000 light-years, respectively, but there are many others. Astronomers have discovered more than 50 satellite galaxies orbiting the Milky Way. Most of them are faint dwarf spheroidal galaxies, small collections of old stars with very little gas or dust. Some contain only a few thousand stars, making them more like giant star clusters than true galaxies. These satellite galaxies are important because they're laboratories for studying dark matter. Many of them seem to be dominated by dark matter, with the mass of the invisible dark matter far exceeding the mass of the visible stars. By studying the motions of stars within these galaxies, astronomers can constrain the properties of dark matter and test different theoretical models. Some of these satellite galaxies are being torn apart by the Milky Way's tidal forces. As they orbit, streams of stars are pulled away, creating long ribbons of stellar debris that wrap around the galaxy. These stellar streams are like fossils, preserving information about past interactions and helping astronomers reconstruct the history of the Milky Way's growth. And here's something mind-blowing. We're still discovering new satellite galaxies. As our surveys improve and we develop better techniques for detecting faint, diffuse objects, we keep finding more and more of these tiny companions. Some are so faint that they were only discovered in the last few years. This raises an interesting question. How many satellite galaxies does the Milky Way actually have? Current theoretical models predict that there should be hundreds, possibly even thousands, of small dark matter halos orbiting our galaxy. But we've only found a few dozen that contain visible stars. Where are all the others? This is known as the missing satellites problem, and it's one of the puzzles that keeps astronomers up at night. Maybe the missing satellites are there, but they're so faint that we can't detect them yet. Or maybe something about the physics of star formation prevents small dark matter halos from forming many stars. Or maybe our understanding of dark matter needs to be revised. It's a mystery, and like all good mysteries, it drives us to keep exploring, keep observing, and keep questioning our assumptions. Now, let's talk about something that connects everything we've discussed so far. The concept of the galactic ecosystem. The Milky Way isn't a static object. It's a living, breathing ecosystem where matter cycles through different phases over millions and billions of years. Stars are born from clouds of gas and dust. They live their lives, fusing hydrogen into heavier elements in their cores, and when they die, they return that enriched material back into the interstellar medium, either gently through stellar winds or violently through supernova explosions. This recycled material becomes part of new clouds which collapse to form new generations of stars. Those stars, in turn, create even heavier elements and eventually return them to space. With each generation, the interstellar medium becomes more enriched with heavy elements, a process that astronomers call chemical evolution. Above and below the galactic plane, this ecosystem extends into 3 dimensions. Gas flows up into the halo, driven by supernova explosions and stellar winds. It cools, falls back down, and triggers new bursts of star formation. Cosmic rays accelerated in the disk escape into the halo, carrying energy with them. Magnetic fields thread through everything, guiding the flow of charged particles and influencing the structure of the interstellar medium. And all of this is happening not just in isolation, but in the context of the larger cosmic web. The Milky Way is part of a group of galaxies called the Local Group, which includes Andromeda, Triangulum, and dozens of smaller galaxies. The Local Group itself is part of a larger structure called the Virgo supercluster, which contains thousands of galaxies spread across tens of millions of light years. But even that's not the whole picture. Recent surveys have revealed that the Virgo supercluster is actually just one lobe of an even larger structure called Laniakea, which means immeasurable heaven in Hawaiian. Laniakea is a supercluster of superclusters, containing about 100,000 galaxies with a total mass of roughly 100 million billion times the mass of the Sun. The Milky Way, our home galaxy, is located near the outer edge of Laniakea, flowing along with countless other galaxies toward a gravitational center known as the Great Attractor. And Laniakea itself is being pulled toward an even larger structure called the Shapley supercluster. It's structures within structures, all the way up, a cosmic hierarchy that extends from the scale of planets to the scale of the observable universe itself. When you look up at the night sky and wonder what exists above and below our solar system, you're really asking about our place in this vast cosmic architecture. And the answer is humbling. We're part of something unimaginably large, complex, and interconnected. But let's bring things back to a more human scale for a moment. Let's talk about what all of this means for us. Right here, right now, every atom in your body has a story. The hydrogen atoms were mostly created in the Big Bang, about 13.8 billion years ago. The carbon, nitrogen, and oxygen atoms were forged in the cores of stars that lived and died before our sun was born. The heavier elements, like the iron in your blood, were created in supernova explosions or in the collisions of neutron stars. All of these atoms were once floating in the interstellar medium, part of the thin haze of gas and dust that fills the space between stars. Gravity gathered them together into a cloud, and that cloud collapsed to form our solar system about 4.6 billion years ago. The sun ignited at the center, and the leftover material coalesced into planets, moons, asteroids, and comets. On one of those planets, something remarkable happened. The atoms organized themselves into molecules, and those molecules organized themselves into cells, and those cells organized themselves into complex life forms. Over billions of years, life evolved, diversified, and eventually produced creatures capable of looking up at the sky and asking questions about where they came from. That's you. That's us. We are the universe trying to understand itself, and every time we make a new discovery, every time we send a spacecraft to explore a distant world or build a telescope to peer deeper into space, we're writing another chapter in humanity's cosmic story. The discoveries we've made in just the past few years are staggering. The James Webb Space Telescope has revealed galaxies that formed when the universe was only a few 100 million years old. The Event Horizon Telescope has captured the first images of black holes. The LIGO and Virgo detectors have opened up an entirely new way of observing the universe by detecting gravitational waves from colliding black holes and neutron stars. And closer to home, we're making incredible progress in understanding our own solar system. The Perseverance rover is searching for signs of ancient life on Mars. The James Webb Space Telescope has detected carbon dioxide in the atmosphere of an exoplanet, bringing us closer to finding signs of life beyond Earth. And missions like Europa Clipper, launching soon, will explore the icy moons of Jupiter, some of which might harbor subsurface oceans with conditions suitable for life. All of these missions, all of these discoveries, are expanding our understanding of what exists above and below our solar system and what our place is in the grand cosmic story. But there's still so much we don't know. And that's the exciting part. We don't know what dark matter is made of. We've never directly detected a dark matter particle despite decades of searching. We know it's there because of its gravitational effects, but its fundamental nature remains a mystery. We don't fully understand dark energy, the mysterious force that's causing the expansion of the universe to accelerate. Dark energy makes up about 68% of the total energy content of the universe, yet we have no idea what it actually is. We don't know if there's life elsewhere in the universe. We've found thousands of planets orbiting other stars, and many of them are in the habitable zone where liquid water could exist on their surfaces. But we haven't yet found definitive evidence of life beyond Earth. That could change in the next few years, though, as new telescopes come online, and we develop better techniques for analyzing the atmospheres of distant planets. We don't know if the laws of physics are the same everywhere in the universe. We assume they are, and all of our observations so far support that assumption. But what if there are regions of space where the fundamental constants of nature are slightly different? What would that mean for our understanding of the universe? We don't know what happened before the Big Bang, or if that question even makes sense. Our current theories break down at the very beginning, at the moment when time and space themselves came into existence. These are profound questions, and they don't have easy answers. But that's what makes science so exciting. We're not just learning facts. We're pushing the boundaries of human knowledge, venturing into uncharted territory, and discovering things that no one has ever known before. And you can be part of this adventure. You don't have to be a professional astronomer or physicist to contribute to our understanding of the universe. Citizen science projects allow anyone with an internet connection to help analyze data from telescopes, search for exoplanets, or classify galaxies. Amateur astronomers make important discoveries all the time, from spotting new comets to detecting supernovae in distant galaxies. Even if you don't contribute directly to research, you can still be part of the story by staying curious, asking questions, and sharing your sense of wonder with others. Talk to your friends and family about the amazing discoveries being made. Encourage young people to pursue careers in science and engineering. Support funding for scientific research and space exploration, because ultimately, this is a human endeavor. We're all in this together, inhabitants of a small planet orbiting an ordinary star in one of the spiral arms of an ordinary galaxy. But there's nothing ordinary about our ability to look up, ask questions, and seek answers. Let's talk about some specific missions and observations that are helping us answer the question, of what exists above and below our solar system. One of the most important tools in modern astronomy is the Gaia spacecraft, which I mentioned earlier. Gaia is a European Space Agency mission that launched in 2013 with the goal of creating the most precise three-dimensional map of the Milky Way ever made. Gaia measures the positions, distances, and motions of over 1 billion stars with unprecedented accuracy. It can detect the apparent motion of a star across the sky with a precision equivalent to measuring the width of a human hair from a distance of 1,000 kilometers. It's an astonishing technical achievement. The data from Gaia has revolutionized our understanding of the Milky Way's structure. By mapping out where stars are and how they're moving, astronomers have discovered new streams of stars, identified populations with unusual kinematics, and traced the history of the galaxy's assembly over billions of years. One of the most exciting discoveries from Gaia is the detection of the Radcliffe wave, a massive undulating structure of gas and dust extending above and below the galactic plane. The Radcliffe wave is about 9,000 light-years long and contains several million times the mass of the Sun. It's shaped like a sine wave, oscillating up and down relative to the galactic plane. The discovery of the Radcliffe wave was made possible by combining Gaia's precise distance measurements with maps of molecular clouds. It turns out that many of the nearby star-forming regions, including famous sites like the Orion Nebula, are all part of this single coherent structure. The Radcliffe wave is probably the result of a past disturbance, perhaps a supernova explosion or the passage of a dwarf galaxy that sent ripples propagating through the gas in the galactic disk. It's a reminder that the galaxy is full of dynamic structures that we're only beginning to understand. Another mission that's contributing to our understanding of the space above and below our solar system is the Hubble Space Telescope. Hubble has been observing the universe for over 3 decades now, and it continues to make important discoveries. One of Hubble's key contributions has been the study of the galactic halo. By observing distant quasars and analyzing how their light is absorbed by gas in the Milky Way's halo, astronomers have been able to map out the distribution and properties of this hot diffuse gas. What they've found is that the halo is filled with million-degree gas, heated by supernova explosions and other energetic processes. This hot halo extends out to at least 200,000 light-years from the galactic center, forming a massive reservoir of material that feeds ongoing star formation in the disk. Hubble has also been instrumental in studying high-velocity clouds. By measuring the chemical composition of these clouds, astronomers can determine whether they're primordial gas falling onto the galaxy for the first time or recycled material that was previously enriched by stars. The James Webb Space Telescope, which began science operations in 2022, is now joining Hubble in exploring these questions. Webb's infrared capabilities allow it to peer through dust and observe objects that are too cool or too distant for visible light telescopes to see. Webb has already made groundbreaking observations of the early universe, detecting galaxies that formed when the cosmos was only a few 100 million years old. But it's also making important contributions closer to home, studying star-forming regions within the Milky Way, analyzing the atmospheres of exoplanets, and, as we discussed earlier, examining interstellar objects like 3I/Atlas. One of Webb's key advantages is its ability to perform spectroscopy, breaking down light into its component wavelengths to reveal the chemical fingerprints of distant objects. This allows astronomers to determine what things are made of, how hot they are, and how fast they're moving, all without ever visiting them directly. Future missions will push these capabilities even further. The Nancy Grace Roman Space Telescope, expected to launch in the late 2020s, will have a field of view 100 times larger than Hubble's, allowing it to survey vast swaths of the sky quickly. Roman will be particularly valuable for studying the structure of the Milky Way's halo and detecting faint dwarf galaxies. Ground-based observatories are also getting dramatic upgrades. The extremely large telescope, currently under construction in Chile, will have a primary mirror 40 meters in diameter, making it the largest optical telescope ever built. With this enormous light-collecting area, the ELT will be able to study faint objects in unprecedented detail, from distant galaxies to the atmospheres of nearby exoplanets. And then there are the radio telescopes. The Square Kilometre Array, an international project to build the world's largest radio telescope, will revolutionize our understanding of the universe at radio wavelengths. It will be able to map the distribution of neutral hydrogen throughout the Milky Way and beyond, revealing the structure of the cosmic web in exquisite detail. All of these instruments, working together across different wavelengths and using different techniques, are painting an increasingly complete picture of what exists above and below our solar system. But let's zoom out one more time and think about the very largest scales. What exists in the space perpendicular to the galactic plane when you go really far out? If you could travel millions of light years straight up from the Milky Way, you'd eventually reach the outer boundaries of the local group, the gravitational association of galaxies that includes the Milky Way and Andromeda as its two largest members. The local group spans about 10 million light-years across and contains more than 80 known galaxies, though most of them are small dwarf galaxies. The Milky Way and Andromeda are by far the dominant members, with Triangulum being a distant third. But here's something fascinating. The Milky Way and Andromeda are on a collision course. They're currently moving toward each other at about 110 kilometers per second, and they're expected to collide in about 4.5 billion years. When galaxies collide, the stars themselves rarely hit each other because the distances between stars are so vast compared to their sizes. But the gravitational interactions between the two galaxies will completely reshape both of them. The spiral structures will be disrupted, and over billions of years, the two galaxies will merge to form a single, giant elliptical galaxy. Some astronomers have nicknamed this future galaxy Milkomeda. Don't worry about Earth, though. By the time this collision happens, the Sun will already be nearing the end of its life, and our planet will have long since become uninhabitable due to the Sun's gradual increase in luminosity. The galaxy merger is one of the least of our long-term worries. Continue traveling outward, beyond the local group, and you'd enter the space between galaxy groups. This is where the large-scale structure of the universe becomes really apparent. You'd see filaments of galaxies stretching across hundreds of millions of light years. Separated by vast voids with very few galaxies in them, the distribution of galaxies isn't random. It's organized into this cosmic web structure, shaped by the gravitational influence of dark matter over billions of years of cosmic evolution. The filaments mark out the densest regions where dark matter is concentrated. Galaxies form preferentially in these regions because that's where there's enough matter to collapse under gravity. The voids, meanwhile, are regions where dark matter is sparse. There are still some galaxies in the voids, but they tend to be smaller, less massive, and less active in terms of star formation compared to galaxies in the filaments. This large-scale structure contains crucial information about the history and fate of the universe. By mapping out how galaxies are distributed in space, astronomers can test cosmological models and constrain the properties of dark matter and dark energy. One of the most ambitious projects to map this structure is the Dark Energy Spectroscopic Instrument, or DESI, which began its main survey in 2021. DESI is measuring the distances to tens of millions of galaxies. creating a three-dimensional map of the universe that extends back billions of years in time. Because light takes time to travel, when we observe distant galaxies, we're seeing them as they were in the past. By mapping galaxies at different distances, we're essentially creating a time-lapse movie of cosmic evolution. We can see how the large-scale structure has changed over time, how galaxies have evolved, and how the expansion of the universe has been influenced by dark energy. DSI's early results, released in 2024, have already hinted at some intriguing possibilities. The data suggests that dark energy might not be constant as most models assume, but could instead be changing over time. If confirmed, this would be a revolutionary discovery, forcing us to rethink our understanding of the universe's evolution and ultimate fate. But these results are still preliminary, and scientists are being careful not to jump to conclusions. More data and more analysis are needed before we can say for certain whether dark energy is truly evolving or whether we're seeing some subtle systematic effect in the measurements. This is how science works. We make observations, we analyze the data, we propose hypotheses and we test them. Sometimes our ideas are confirmed and sometimes they're overturned by new evidence. But every step forward, even when it leads to more questions, brings us closer to the truth. Now, let's talk about something that might seem unrelated at first, but is actually deeply connected to everything we've discussed: the concept of multi-ascendure astronomy. For most of human history, astronomy was limited to observing visible light, the stars, planets, and galaxies we could see with our eyes or through telescopes were the extent of our knowledge about the universe. But in the 20th century, astronomers learned to observe at other wavelengths: radio waves, infrared, ultraviolet, X-rays, and gamma rays. Each wavelength reveals different phenomena. Radio waves show us cold gas and pulsars. Infrared penetrates dust to reveal star formation. X-rays trace hot gas and energetic processes around black holes. Gamma rays come from the most violent explosions in the universe. This multi-wavelength approach transformed our understanding of the cosmos. But in the 21st century, we've added entirely new types of messengers: neutrinos and gravitational waves. Neutrinos are nearly massless particles that barely interact with matter. They're produced in nuclear reactions like those in the core of the Sun or in supernova explosions. Because they interact so weakly, they can travel through vast amounts of matter without being absorbed or deflected. This makes them incredibly difficult to detect, but also incredibly valuable because they carry information from deep inside objects where light can't escape. Gravitational waves are ripples in the fabric of space-time itself, produced by the most cataclysmic events in the universe: colliding black holes, merging neutron stars, and possibly even the Big Bang itself. They were predicted by Einstein's theory of general relativity, but not directly detected until 2015, when the LIGO observatories registered the signal from two black holes spiraling together and merging. By combining observations from electromagnetic radiation, neutrinos, and gravitational waves, we can study cosmic events in unprecedented detail. This is multi-ascendure astronomy, and it's opening up entirely new ways of exploring the universe. For example, in 2017, LIGO and Virgo detected gravitational waves from a neutron star merger. Within seconds, telescopes around the world were alerted, and dozens of observatories swung into action to observe the event at different wavelengths. They detected a gamma-ray burst, followed by a fading optical and infrared counterpart, and eventually radio emission. This single event, observed in gravitational waves, gamma rays, X-rays, optical, infrared, and radio, taught us more about neutron star mergers than decades of theoretical work. It confirmed that these mergers are the primary sites where heavy elements like gold and platinum are created. It provided a new way to measure the expansion rate of the universe. and it tested general relativity in extreme conditions where the theory had never been verified before. Now, you might be wondering what all of this has to do with the question of what exists above and below our solar system. The connection is this: all of these phenomena, from gravitational waves to high-velocity clouds, from cosmic rays to interstellar objects, are part of the same cosmic ecosystem. They're all connected by physical processes that operate across vast scales of space and time. The supernova that creates heavy elements also accelerates cosmic rays and launches high-velocity clouds into the galactic halo. The merger of neutron stars that produces gravitational waves also creates a kilonova that enriches the interstellar medium with precious metals. The accretion of gas onto the Milky Way from the intergalactic medium feeds star formation, which in turn produces stellar winds and supernovae that drive gas back out into the halo. Understanding what exists above and below our solar system means understanding these interconnections. It means seeing the big picture, recognizing that we're part of a vast, dynamic, evolving system that extends from the smallest subatomic particles to the largest structures in the observable universe. And here's something that really drives home the interconnectedness of everything. The atoms in your body have traveled through this system multiple times. Think about it. The carbon in your cells was created in the core of a star through nuclear fusion. When that star died, perhaps in a supernova explosion, that carbon was ejected into the interstellar medium. It might have floated through space for millions of years, part of a diffuse cloud of gas and dust. Eventually, gravity caused that cloud to collapse, forming a new generation of stars. Maybe our sun was one of those stars, or maybe the carbon atom went through several more cycles, being incorporated into stars and then ejected again, each time becoming part of a gas cloud that was slightly more enriched with heavy elements. Finally, about 4.6 billion years ago, that carbon atom became part of the molecular cloud that collapsed to form our solar system. It was incorporated into the disk of material around the young sun, and eventually it became part of Earth. On Earth, the carbon atom cycled through different forms. It might have been part of the atmosphere as carbon dioxide, then absorbed by a plant through photosynthesis, and incorporated into organic molecules. Maybe it was part of an ancient tree that was buried and turned into coal, or part of a marine organism whose shell sank to the ocean floor and was buried in sediment, eventually becoming limestone. Over billions of years, through plate tectonics and erosion, weathering and volcanic activity, that carbon atom cycled through Earth's various reservoirs, the atmosphere, the oceans, the crust, the mantle. And at some point in the recent past, it became part of your body. Maybe it's in your DNA right now, or in a protein, or just floating in your bloodstream as part of a glucose molecule. Eventually, through respiration or excretion or decomposition, that carbon atom will leave your body and continue its journey. It might become part of another organism, or dissolve in the ocean, or be released into the atmosphere. And billions of years from now, when the sun dies and expands into a red giant, that atom might be ejected back into space, ready to begin the cycle again in some future solar system. This is your connection to the cosmos. You are literally made of stardust, and that stardust has been on an epic journey through space and time. The question of what exists above and below our solar system is also the question of where you came from and where you're going. Now let's talk about some of the more speculative aspects of what might exist in the space perpendicular to the galactic plane. One intriguing possibility is the existence of isolated or rogue planets. These are planets that aren't orbiting any star. They either formed independently in interstellar space, though current theories suggest this is unlikely for objects larger than about 13 Jupiter masses, or, more commonly, were ejected from their home solar systems through gravitational interactions. Computer simulations of planetary system formation suggest that ejections are fairly common, especially in systems with multiple giant planets. The gravitational interactions between these massive worlds can lead to chaotic dynamics, and sometimes one planet gets flung out of the system entirely, doomed to wander through interstellar space forever. How many rogue planets are there? We don't know for sure, but some estimates suggest there could be billions of them in our galaxy, possibly outnumbering stars. They're extremely difficult to detect because they don't emit much light of their own and they're not illuminated by a nearby star. However, astronomers have detected a handful of candidate rogue planets using a technique called gravitational microlensing. When a massive object passes between us and a more distant star, its gravity bends the light from that star, causing a brief brightening. By analyzing the details of these microlensing events, astronomers can sometimes determine the mass of the lensing object, and occasionally these objects are too small to be stars, but too massive to be anything other than planets. Some rogue planets might have been ejected when they were still quite young and hot, and these would still be emitting infrared radiation that telescopes like Webb could potentially detect. Others might be warmed by the decay of radioactive elements in their interiors, or by tidal heating if they have large moons. It's even possible that some rogue planets could harbor life. If a planet were ejected from its home system after life had already evolved on it, and if it had a thick enough atmosphere to trap heat from the planet's interior, it might be able to maintain liquid water beneath an icy surface. This is speculative, of course, but it's not physically impossible. Imagine there could be worlds out there wandering in the dark between the stars, carrying ecosystems beneath their frozen surfaces, completely isolated from any sun. It's a haunting and beautiful idea. Another speculative possibility is the existence of primordial black holes in the space above and below the galactic plane. Primordial black holes are different from the black holes that form from collapsing stars. They're hypothesized to have formed in the very early universe, within the first second after the Big Bang, from tiny fluctuations in density. If these fluctuations were strong enough, regions of space could have collapsed directly into black holes without ever forming stars first. Primordial black holes could have a wide range of masses, from less than the mass of an asteroid to thousands of times the mass of the Sun, and importantly, they're one of the candidates for dark matter. If primordial black holes exist and make up a significant fraction of dark matter, there could be millions or even billions of them scattered throughout the Milky Way's halo, including in the space above and below the galactic plane. Most would be too small to have any noticeable effect on their surroundings, but occasionally one might pass through the solar system or near enough for us to detect its gravitational influence. Astronomers are searching for primordial black holes using several techniques. Gravitational microlensing can detect them if they pass in front of distant stars. Gravitational wave detectors might pick up the signals from primordial black holes merging with each other. And if a small primordial black hole were to pass through a star or planet, it could leave distinctive signatures that we might be able to observe. So far, there's no definitive evidence for primordial black holes, but the search continues. If they do exist, they would be relics from the very beginning of time, fossils from the Big Bang itself, silently drifting through the galaxy and shaping its evolution through their gravitational influence. Let's talk about another speculative but fascinating topic: the possibility of extraterrestrial intelligence. We've talked about the structure of the galaxy, the clouds of gas and dust, the stars and planets, the cosmic rays and magnetic fields. But what about life? What about intelligence? Could there be other civilizations out there, above or below the galactic plane, looking up at their own night skies and asking the same questions we are? This is the realm of SETI, the search for extraterrestrial intelligence. For decades, scientists have been using radio telescopes to search for signals from alien civilizations. The idea is that any technological civilization would likely develop radio communication, and some of those transmissions might escape into space where we could potentially detect them. So far, despite thousands of hours of observation time, we haven't found any convincing signals. This doesn't mean there aren't any civilizations out there. It just means that if they exist, they're either very far away, not broadcasting in ways we can detect, or perhaps not interested in communicating with us. The famous Fermi paradox encapsulates this puzzle. Given the age of the universe and the vast number of stars and planets, we might expect intelligent life to be fairly common. So where is everybody? There are many proposed solutions to the Fermi paradox. Maybe intelligent life is extremely rare. Maybe civilizations tend to destroy themselves shortly after developing advanced technology. Maybe they're out there but intentionally hiding. Maybe they've moved beyond radio communication to something we can't detect yet. Maybe the distances are just too vast for communication to be practical. Or maybe, just maybe, we're among the first. Maybe we're one of the early civilizations in the galaxy, and it's our destiny to be the explorers and the question askers, the ones who spread out into the cosmos and wonder why it's so quiet. It's a profound question with no easy answer, but the search continues. New surveys are scanning larger portions of the sky at more wavelengths. The Breakthrough Listen initiative is conducting the most comprehensive SETI search ever undertaken, and as we discover more exoplanets and characterize their atmospheres, we're developing techniques that might allow us to detect biosignatures, chemical fingerprints of life, even if that life isn't technologically advanced. The space above and below our solar system might harbor other intelligences, other beings looking out at the cosmos and asking the same questions we are. We don't know yet, but the very fact that we can ask the question, that we can search for the answer, is remarkable in itself. Let's shift gears again and talk about time. When you look up at the night sky, you're not just looking across space, you're looking back in time. Light takes time to travel, so when you see a star that's 1,000 light years away, you're seeing it as it was 1,000 years ago. The light that's entering your eye right now left that star before the Norman Conquest, before the printing press, before Columbus sailed to the Americas. The farther out you look, the farther back in time you see. The Andromeda Galaxy, visible as a faint smudge to the naked eye on a dark night, is about 2.5 million light years away. The light you see from Andromeda left that galaxy before humans evolved, when our ancestors were small-brained apes roaming the African savanna. The most distant galaxies we've detected are over 13 billion light years away. We're seeing them as they were when the universe was only a few 100 million years old, shortly after the very first stars began to shine. This has profound implications for understanding what exists above and below our solar system. When we map the structure of the galaxy, we're not seeing it as it is now. We're seeing different parts of it at different times in the past. The stars directly above and below us, just a few 100 light years away, we're seeing as they were a few centuries ago. The structures farther out in the halo, thousands of light years away, we're seeing as they were during ancient civilizations on Earth. And the distant galaxies in the cosmic web, we're seeing as they were billions of years before Earth even existed. This means our picture of the universe is always incomplete in a fundamental way. We can never see the universe as it is right now. We can only see it as it was, and different parts of what we observe existed at different times. It's like looking at a family photo album where each picture was taken at a different decade, but they're all laid out on the table in front of you at the same time. You're seeing your grandmother as a child, your parents as teenagers, and yourself as an adult, all simultaneously. That's what observing the universe is like. This time delay effect becomes especially important when we think about cosmic evolution. The universe isn't static, it's changing. Stars are being born and dying, galaxies are colliding and merging. The cosmic web is being shaped by gravity and dark energy. When we observe distant objects, we're seeing the universe as it was when it was younger. By comparing nearby objects to distant ones, we can trace how things have changed over cosmic time. We can see how galaxies have evolved, how star formation rates have changed, how the abundance of heavy elements has increased as generations of stars have lived and died. This is one of the most powerful tools in modern cosmology, using the finite speed of light as a time machine to peer into the past and understand how the universe has evolved to its present state. But here's something that might blow your mind. While we can look back in time by observing distant objects, we can never see the future. There's a fundamental horizon to our observations, a limit beyond which we can never see. No matter how powerful our telescopes become, this horizon exists because the universe is expanding, and that expansion is accelerating due to dark energy. There are regions of space so far away that their recession velocity exceeds the speed of light. Light from those regions can never reach us because the space between us and them is expanding faster than light can cross it. This defines what's called our observable universe, the sphere of space from which light has had time to reach us since the Big Bang. The radius of this sphere is about 46 billion light-years, which is larger than 13.8 billion light-years because space has been expanding while the light was traveling. If you made this far, please subscribe to the channel. Your support means a lot to this community. Beyond this observable universe, there's presumably more universe, more galaxies, more stars, more planets. But we can never see them, never observe them, never know anything about them. They exist in a region of space that is causally disconnected from us, and due to the accelerating expansion driven by dark energy, this observable universe will actually get smaller in the future. Galaxies that we can see now will eventually recede beyond our horizon and disappear from view. Trillions of years from now, if any civilizations exist in our local group, they'll look out and see only their own nearby galaxies. All the distant galaxies, all the evidence of the Big Bang and cosmic expansion will have vanished beyond the horizon. Those future astronomers, if they don't have our historical records, might conclude that the universe consists only of their local group of galaxies surrounded by infinite empty space. They would have no way of knowing about the billions of other galaxies that once populated their sky. It's a sobering thought. We live at a special time in cosmic history when we can still see the large-scale structure of the universe and deduce the story of its evolution. In a sense, we're lucky to exist now, when the evidence of our cosmic origins is still visible. But let's return from these cosmic scales to something a bit closer to home. Let's talk about what all of this means for the future of humanity. Understanding what exists above and below our solar system isn't just an academic exercise. It has practical implications for our future as a species. For one thing, the resources of the solar system are finite. Earth is a closed system with limited supplies of many elements and materials. If humanity is going to continue expanding and developing, we'll eventually need to look beyond Earth for resources. Asteroids, many of which orbit in the space above and below the ecliptic plane, contain vast amounts of valuable materials: iron, nickel, platinum group metals, water ice, and more. A single metallic asteroid could contain more platinum than has been mined in all of human history. The high-velocity clouds and interstellar gas we've discussed might seem too diffuse to be useful, but understanding them helps us understand the long-term evolution of the galaxy and where resources will be available in the future. If humanity ever expands beyond our solar system to other stars, we'll need to navigate through this interstellar medium, and understanding its properties will be crucial. The cosmic rays that permeate the space above and below the solar system are both a hazard and a resource. They're a hazard because they pose a radiation risk to astronauts and spacecraft electronics, but they're also a resource for understanding the universe and learning how to shield against them or even harness their energy could be important for future space exploration. The magnetic fields that thread through the galaxy will affect any interstellar journey. Understanding their structure and properties will be essential for planning long-duration missions beyond our solar system. And then there's the ultimate question: are we alone? The search for extraterrestrial life, whether microbial life on Mars or Europa, biosignatures in the atmospheres of exoplanets, or technological signals from distant civilizations, is one of the most profound scientific endeavors of our time. Finding life elsewhere would fundamentally change our perspective on our place in the universe. It would answer one of humanity's oldest questions and raise countless new ones. And the search for that life necessarily involves understanding what exists in the space around us, above and below our solar system and beyond. But even beyond these practical considerations, there's something deeper at stake. Understanding the universe is part of what makes us human. The drive to explore, to question, to seek knowledge, this is fundamental to our nature. Every ancient culture looked up at the sky and created stories to explain what they saw. They saw patterns in the stars and wove them into myths and legends. They tracked the movements of the planets and developed calendars. They wondered about their place in the cosmos. We're still doing the same thing, just with more sophisticated tools. We're still looking up, still asking questions, still seeking to understand our place in the grand scheme of things. And what we've learned is both humbling and empowering. We've learned that we're incredibly small, tiny organisms on a tiny planet, orbiting an ordinary star in an ordinary galaxy in a vast universe containing hundreds of billions of galaxies. But we've also learned that we're incredibly special. We're made of atoms that were forged in the hearts of stars. We're the product of billions of years of cosmic evolution. We're the universe becoming conscious of itself, able to look back across space and time and understand where we came from. The space above and below our solar system is part of our heritage. The gas clouds, the stars, the cosmic rays, the magnetic fields, they all played a role in creating us. We're not separate from the universe, we're an integral part of it. And that means the future of the universe is, in a small way, up to us. We have the ability to shape what happens next, at least in our corner of the cosmos. We can choose to be responsible stewards of our planet. We can choose to extend our reach into space. We can choose to preserve knowledge and pass it on to future generations. We can choose to ask questions and seek answers. Let me share one more perspective that ties everything together. In the 1970s, astronomer Carl Sagan helped design a message that was placed aboard the Voyager spacecraft. The message consisted of a golden record containing sounds and images from Earth, intended for any extraterrestrial intelligence that might someday encounter the spacecraft. Voyager 1 and Voyager 2 have now left the solar system and entered interstellar space. They're moving upward and outward from the galactic plane, carrying their messages into the vast unknown. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 45. In about 300,000 years, Voyager 2 will pass near Sirius, the brightest star in our night sky. These spacecraft, these tiny emissaries from humanity, are now part of the interstellar medium we've been discussing. They're traveling through the same space that contains high-velocity clouds, cosmic rays, magnetic fields, and interstellar dust. They're moving through the space above and below the galactic plane that we've spent so much time exploring in this conversation, and they carry with them a message, not just for potential aliens, but for ourselves. We are here, we exist, we think and wonder and create. We've looked up at the universe and tried to understand it. We've built these machines and sent them out into the cosmos as proof of our existence and our curiosity. The golden records on the Voyager spacecraft include a diagram showing Earth's location in the galaxy. It uses the positions of pulsars, rapidly rotating neutron stars that emit regular pulses of radio waves, as a kind of cosmic GPS. Any civilization that finds the record and decodes the diagram could, in theory, trace the lines back to their intersection point and find our solar system. But here's the beautiful irony. By the time any alien civilization finds one of the Voyager spacecraft, the information on that diagram might be outdated. The stars move, the pulsars slow down, the galaxy evolves. The solar system is orbiting the galactic center, remember, completing one orbit every 225 to 250 million years. So even our attempts to mark our place in the universe are temporary. Everything is in motion. Everything is changing. The universe doesn't stand still for anyone, and that's okay. That's the nature of reality. We exist in a dynamic, evolving cosmos, and we're part of that evolution. We're not eternal observers standing outside the system. We're participants in the grand cosmic drama, the space above and below our solar system. The structures we've explored in this conversation are all part of that drama. They're part of the ongoing story of matter and energy organizing themselves into increasingly complex forms, from simple hydrogen gas to stars to planets to life to consciousness. And that story continues. Right now, at this very moment, new stars are being born in molecular clouds throughout the galaxy. Planets are forming around those stars. Asteroids are colliding. Cosmic rays are striking atmospheres. High-velocity clouds are raining down onto the galactic disk. The Milky Way is slowly cannibalizing the Sagittarius Dwarf galaxy. Andromeda's getting closer, day by day. All of this is happening in the space above and below our solar system, all around us all the time. The universe is not a static photograph. It's a living, breathing, evolving system, and we're part of it. Now, let me address something that we've touched on but haven't fully explored: the role of simulation and modeling in understanding what exists above and below our solar system. Direct observation gives us snapshots of the universe at different times and places, but to really understand how everything works together, we need models. We need computer simulations that can take the fundamental laws of physics and run them forward through billions of years of simulated time to see what happens. These simulations are incredibly sophisticated. Modern cosmological simulations can model the evolution of the entire universe from shortly after the Big Bang to the present day. They include dark matter, ordinary matter, gravity, gas dynamics, star formation, supernova feedback, black hole growth, and more. The results are stunning. These simulations produce galaxies that look remarkably similar to real observed galaxies. They reproduce the large-scale structure of the universe, the filaments and voids we talked about earlier. They predict the properties of the circumgalactic medium and the galactic halo, which can then be tested against observations. But simulations also reveal things that are difficult or impossible to observe directly. For example, they can show us what the dark matter halo looks like. Remember, dark matter doesn't emit light, so we can only infer its presence from its gravitational effects. But in simulations, we can see the dark matter directly. These simulations show that dark matter halos are not smooth and uniform. They're lumpy and structured, with dense regions and less dense regions. They contain subhalos, smaller concentrations of dark matter that are the remnants of smaller galaxies that merged with the Milky Way in the past. Some of these subhalos still contain visible stars and gas. These are the dwarf satellite galaxies we've observed. But simulations predict that there should be many more dark matter subhalos than we've found satellite galaxies. This is called the missing satellites problem. There are several possible solutions. Maybe there really are many small galaxies out there that we just haven't detected yet because they're so faint. Maybe something prevents stars from forming efficiently in small dark matter halos. Or maybe our understanding of dark matter is incomplete, and it behaves differently on small scales than we currently think. This is an active area of research, and observations from telescopes like Vera Rubin Observatory, which will conduct a deep, wide survey of the sky starting in the late 2020s, should help resolve this question. If there are lots of faint dwarf galaxies hiding in the space above and below the galactic plane, Rubin will find them. Simulations also help us understand the history of the Milky Way. By running simulations with different initial conditions and comparing the results to observations of the real Milky Way, astronomers can work backward to figure out what must have happened in the past. For example, simulations have helped confirm that the Milky Way has grown through mergers with smaller galaxies over its history. They've helped identify streams of stars in the halo that are the remnants of these ancient mergers, and they've helped predict what the Milky Way will look like in the future, including its eventual merger with Andromeda. One particularly exciting recent development is the use of machine learning and artificial intelligence to analyze astronomical data and improve simulations. Neural networks can be trained to recognize patterns in huge data sets, identify interesting objects for follow-up observation, and even help improve the physics models used in simulations. For instance, machine learning algorithms have been used to classify galaxies, detect gravitational lenses, find new exoplanets, and identify cosmic rays. As the volume of astronomical data continues to grow, with surveys like Rubin Observatory expected to generate tens of terabytes of data every night, these AI tools will become increasingly essential. But for all the power of simulations and AI, they're ultimately limited by our understanding of the underlying physics. If there are phenomena we don't know about, or if our models are missing important processes, the simulations will be incomplete. This is why observation remains crucial. We need to keep looking, keep measuring, keep testing our theories against reality. The universe is under no obligation to match our expectations, and history has shown repeatedly that nature is more creative and surprising than we can imagine. Let's talk about some of the surprises that observations have revealed over the years, discoveries that forced us to revise our understanding of what exists above and below the galactic plane. One major surprise was the discovery of hypervelocity stars. These are stars moving so fast, over 500 kilometers per second, that they're escaping the Milky Way's gravitational pull entirely. They're being ejected from the galaxy, destined to wander through intergalactic space forever. How do stars get moving that fast? The leading theory is that they were originally part of binary star systems that ventured too close to the supermassive black hole at the center of the galaxy. The intense gravitational field of the black hole disrupted the binary, capturing one star while flinging the other out at tremendous speed. These hypervelocity stars are moving through the space above and below the galactic plane at speeds that would take them from Earth to the Moon in just a few minutes. They're rare, only a few dozen have been confirmed, but they represent a dramatic illustration of the dynamic nature of the galaxy. Another surprise was the Smith Cloud. This is a giant cloud of hydrogen gas, about 11,000 light-years long, that's plummeting toward the Milky Way's disk from the galactic halo. It's expected to collide with the disk in about 30 million years, triggering a burst of star formation. But here's the weird part. The Smith cloud contains heavy elements, suggesting it came from inside the galaxy rather than from intergalactic space. The leading theory is that it was blown out of the galactic disk by supernovae explosions about 70 million years ago, and now it's falling back down. It's part of the galactic fountain we discussed earlier, material cycling between the disk and the halo. Then there's the Monoceros ring, a ring-like structure of stars that wraps around the Milky Way. It was discovered in the early 2000s and caused quite a stir. Some astronomers think it's the remnant of a dwarf galaxy that's being tidally disrupted by the Milky Way. Others think it's not a separate structure at all, but rather a ripple or wave in the galactic disk itself, possibly caused by a small galaxy passing through the disk in the past. The debate continues, with different groups analyzing the data in different ways and reaching different conclusions. This is normal in science. When new, unexpected structures are discovered, it takes time to figure out what they are and how they fit into the bigger picture. Another surprise came from the study of globular clusters. These are ancient, spherical collections of stars that orbit in the Milky Way's halo. They're some of the oldest objects in the galaxy, formed more than 10 billion years ago. For a long time, astronomers thought all the stars in a globular cluster formed at the same time from the same cloud of gas, so they should all have the same chemical composition. But detailed observations revealed something unexpected. Stars in the same globular cluster can have different abundances of certain elements, particularly light elements like carbon, nitrogen, and oxygen.